All right, in this video, we are finding and graphing inverse functions. So the directions say for each function, write the equation of its inverse and then graph both functions on the grid. And so let's start by graphing the original function, starting with log base 4 of x minus 2 plus 5. And so log base 4 is our parent function. And the parent function has a vertical asymptote at x equals 0. And then his x-intercept is a distance of 1 from the asymptote. And then the next point up would be a distance of the base away. And so because our base is 4, his distance is going to be 4 from the asymptote. And so he goes up to the right and then down towards the asymptote. This particular function has shifted right 2 and up 5. And so the only thing that's going to affect the vertical asymptote is right 2. So I'll go ahead and shift everything right 2. And then shifting up 5, we're just going to take those 2 points and shift them up 5 units. And so our x-intercept was at 0. Now it's at 5. And then still going down towards the asymptote. And so to find the inverse function, we could start by graphing it by just switching the x and y of each of our ordered pairs. But I want to review how to do it algebraically. And so when you are solving for an inverse algebraically, you want to get rid of the f of x notation and use a y instead. It's the same thing, but we're going to switch our x and y variables and then resolve for the y. Okay, and so switch your x and y first. So now y is inside the log. And when we resolve for the y, we have to isolate the log first. And so we need to get rid of this plus 5 by subtracting 5. And then once we have isolated the log, you need to convert to exponential form. So to convert, your base is 4, your exponent is x minus 5, and it equals y minus 2. So base 4 to the x minus 5 equals y minus 2. And then our last step is just to add 2 to both sides. And when you add the 2, don't make it part of the exponent. It just stays outside. And so our inverse function is 4 to the x minus 5 plus 2. And so something you may notice about the inverse function and the original function is if you start with a log base 4, you should end with an exponential base 4. If you started with a minus 2 inside, you should end up with a plus 2 outside. And then if you started with a plus 5 outside, you should end up with a minus 5 inside. Everything gets switched around. Okay, so to graph our inverse function, I'll graph in red. An exponential function always starts with the asymptote at y equals 0. And then the y-intercept is always 1 away. And the next point to the right is the base away. So we're working with base 4. And so our next point is a distance of 4 away. The transformations on this graph is right 5, up 2. And so the only thing that affects the horizontal asymptote is moving it up 2. And so I'll start by moving everything up 2. So up 1, up 2. So there's our new horizontal asymptote. And then we need to shift the points right 5. Moving the horizontal line right 5 isn't going to change its location. So right 5, 1, 2, 3, 4, 5. And so an exponential function is growing to the right and then going down towards the asymptote. And so the way to check whether your inverse is correct is it should be a reflection across the y equals x line. And so I find a lot of my mistakes when I don't have that situation happening. And so I always kind of sketch that line in. Some graphs it's harder to tell, and so I also like the algebraic way of checking your work. Okay, next we are dealing with a quadratic function, so let's put that on the graph. And this quadratic function has a domain restriction. Anytime you see a comma with x greater than or equal to or less than or equal to, that they're restricting the domain. And we'll see how that comes into play when we graph it. And so starting with quadratic parent function, we have a vertex at 0, 0. 1 squared is 1, 2 squared is 4. And so we have those same points on each side, and it makes a parabola. Okay, and so this function has been moved left 3, down 1. So we're going to take all our points and move them left 3, down 1. So our new vertex is -3, -1. Now to apply the domain restriction, they're saying less than, and so that means left. And so less than or equal to -3, the -3 line, x equals -3 is right here, and we're saying less than. So we only have the part of the graph that is to the left of that line. So this part's gone. Everything to the left of the vertex remains. And this line isn't actually there. Okay, and so this is our starting function. To find the inverse, let's do it algebraically. So switch our x and y. And then we are resolving for y. So our first step is to add 1 to both sides. And then to get rid of the square, we do the square root property. And so for the square root property, whenever you are adding a square root to undo a square, you have the plus or minus square root. Okay, at this step, write the plus or minus and then go see what your domain restriction is. If it is less than or equal to, you are going to choose the negative square root. And so get rid of the plus sign and we are just working with negative. If it were greater than or equal to, we would just choose the positive square root. That's what that domain restriction is for, telling you which one you want. Okay, and so our last step is just to subtract 3 from both sides. And don't put that 3 under the radical. It doesn't get to join late. And so we have a -3 outside. And so our final answer is negative square root of x plus 1, and then a -3 outside. And so just a quick check of our work is if you are starting with a quadratic that has a less than restriction, you should end with a negative square root. If you have a +3 inside, you should end up with a -3 outside. And if you have a -1 outside, you should end up with a +1 inside. Everything gets switched around. Okay, and so to graph this, I'm starting with the parent function. The square root parent function has a starting point at 0, 0, 1, 1, 4, 2, and he goes up to the right. And so this function, the first thing we have to do is take care of this reflection across the x-axis, and then we will move it left 1, down 3. Okay, so the reflection across the x-axis, these points are going to flip downward, and so this part is gone, and our square root function is now upside down. And then now we can shift it left 1, down 3. So left 1, down 3. And so you can tell that this function is a reflection across the y equals x line. And so each x and y coordinate should just be switched. All right, next we are working with a rational function. And so to graph the parent function, it has a vertical asymptote and a horizontal asymptote at x equals 0 and y equals 0. And so the origin is where they intersect. And this particular function has been moved left 4, up 3. Okay, so the left 4 is what's going to affect the vertical asymptote. So now it's x equals -4. And the up 3 is going to affect the horizontal asymptote. Okay, and so for the parent function, he usually has a point at 1, 1 and -1, -1 with respect to the origin. And so when you shift your asymptotes, that becomes your new origin where they intersect. And then if you have a reflection, instead of having points in quadrants 1 and 3, they're now going to flip to quadrants 2 and 4. And that's regardless of whether it's over the x-axis or y-axis, the same result. So move these points to quadrants 2 and 4, and then just connect following the asymptotes. Okay, and so let's find our inverse algebraically, switch x and y. And then if you have a negative outside a fraction, just put it in the numerator so that he has a place to go. And then resolve for y. And so first step is we want to subtract 3 from both sides. And then to isolate the y, we need to get this y out of the denominator. And so the way we do that is we multiply both sides by this y plus 4. And so we have these two factors on the left now equal to -1 because the y plus 4 canceled. And then we want to divide by the x minus 3 factor to get the y factor by itself. And you don't need the parentheses on the right side. Okay, and so that leaves us with y plus 4 equals -1 over x minus 3. Last step is to subtract the 4 and just leave it outside the fraction. And so our final answer has a -1 over x minus 3 minus 4. And at this point, you can put the negative back outside. Just don't put it in the denominator. And so x minus 3 minus 4. Okay, and so the inverse of a rational function is always going to be another rational function. It's because of the symmetry of this function. And so let's graph it. He has been moved right 3, down 4, kind of checking our work algebraically, noticing our +3 became a -3, +3 outside became a -3 inside, and a +4 inside became a -4 outside. Okay, so right 3 would put the vertical asymptote at +3. And then down 4 would put the horizontal asymptote at -4. And then the reflection across the x-axis is going to put us in quadrants 2 and 4. And so up to the right, down, up, down. So this one's a little bit harder to tell that it's reflected across the y equals x line. But you could kind of look at the intersections of the asymptotes and see that it is. Okay, next we are dealing with an exponential function with a base of 1/2. So that 1/2 is our base. And it has been vertically stretched by 4 and then right 3. And so remember the parent function, the default setting for an exponential function is a horizontal asymptote at y equals 0. And we haven't shifted up or down, so that is going to stay. And so the other default setting is a y-intercept that's 1 away, and then your next point should be the base away. And well, our base is 1/2, and so our next point is only going to be a distance of 1/2 away. Okay, and so when we are vertically stretching by 4, our vertical distances, this 1 and this 1/2, they're going to get scaled by 4. That's what the vertical stretch by 4 does. And so instead of being 1 away, our y-intercept is going to be a distance of 4 away. And then instead of being 1/2 away, 1/2 times 4 would be 2. And so those are our 2 points that we're working with. And so the last thing we need to do is just shift them right 3, which isn't going to affect the horizontal asymptote. So right, this was here. So right 3 would be 1, 2, 3. The y-intercept is now sitting at 3. Okay, and so this one's actually growing to the left and decaying as we go to the right. Anytime you have a base smaller than 1, it's going to be an exponential decay function. All right, for our inverse function, switch x and y. And then to re-solve for y, we need to get rid of the 4 first. And so if you want, you can view this as multiplication by 1/4 instead of dividing by 4, just so we can keep track of our transformations when we graph our inverse function. Okay, and so we are ready to convert to log. We have isolated the exponential, and so to convert to log, we're going to have log base 1/2 of 1/4 x equals y minus 3. So log base 1/2 of 1/4 x equals y minus 3. And then our last step would be to just add the 3 to both sides and make sure it doesn't get inside the log. Can't combine that. Okay, and so log base 1/2 of 1/4 x plus 3. So just checking our work real quick. We're starting with exponential base 1/2. We're ending with log base 1/2. We had a 4 being multiplied outside, so we're going to be dividing by 4 or multiplying by 1/4 inside. And then a minus 3 inside becomes a plus 3 outside. Putting it on the graph, we have log base 4. So default, the parent, has a vertical asymptote at 0. And because we're not shifting left or right, that's going to stay. The next point is our x-intercept, which is usually 1 away. And then the next point up is going to be the base away, and our base is 1/2. And so it's going to be 1/2 away from the asymptote. And so the transformation here, when you have a 1/4 inside, remember everything inside the parentheses is backwards. So you would think that's a horizontal compression by 1/4, but it's actually a horizontal stretch by 4. Everything inside is backwards. It's opposite of what you would expect. And so to horizontally stretch this graph by 4, our horizontal distances of 1/2 and 1 are going to be multiplied by 4. So instead of having a distance of 1 away, it's going to be a distance of 4 away. And then instead of having a distance of 1/2, 1/2 times 4 is 2. So that one next point up is going to be 2 away. And then our last step is to shift up 3. So these points need to move up 3 units. And so our x-intercept is up 1, 2, 3. And then our 2 away point is up 3 as well. Okay, and so this blue graph, don't get confused, it's not part of the red function. And so our log function, he is going to approach the vertical asymptote and then go down towards the right. Whenever you have a log with a base that's smaller than 1, his tail is going to be going up towards the asymptote instead of down towards the asymptote. All right, last one, we are starting with square root. And let's get the parent function, 0, 0, 1, 1, 4, 2. And so that's what the parent function looks like. But this function has been vertically stretched by 2 and then left 6. So we need to vertically stretch it first. And so a vertical stretch by 2 is going to change our vertical distances. So notice we go up 1 over 1, up 1 over 3. So instead of going up 1 over 1, we're going to go up 2 over 1 and then up 2 over 3. It's just changing the vertical distances. And so my horizontal distances are still going to be the 1 and then 3, but the vertical distances are going to be 2 each time. Okay, and so up 2 over 1, up 2 over 3 for that 4. And if you wanted the 9, you would go up 2 over 9 if you want a other point. So there's our vertically stretched square root function. So now we just need to move this to the left 6. So instead of being at 0, 0, he's at -6, 0. Okay, finding the inverse, switch x and y. And then resolve for y. So our first step is to get rid of multiplication by 2. And so let's view that as multiplication by 1/2 so that we can keep track of transformations. And then to get rid of a square root, we square both sides. And I wouldn't actually square that 1/2 because we want to really preserve as much of the transformations as possible. And then last step is to subtract 6. Okay, and so our inverse function is 1/2 x squared minus 6. And so just checking our work, if you are starting with square root, you are ending with square. And then if you have a times 2 multiplication by 2 outside, you're going to have multiplication by 1/2 inside. A +6 inside is going to become a -6 outside. And so one other thing we have to do is restrict the domain of this quadratic function, because we know a quadratic function is a parabola, and this function is not parabolic. It is only part of the parabola. And so when you are starting with a positive square root that's opening up, you want to restrict your quadratic to only the right side. And so if this was a negative square root, you would restrict to the left side. Okay, and so our restriction here is only going to be the right side of the vertex. And so this vertex has an x-coordinate of 0. And so to say we want to stay to the right of that 0, we say x is greater than or equal to. So we need to restrict the domain so that we only have the right side. Otherwise, our graphs will not be reflections across y equals x. Okay, and so to graph this, our quadratic parent function starts at 0, 0, 1, 1, 2 squared is 4. And then if you want to do the 3 squared is 9. And we're only doing the right side, so I'm not even going to put the other points on there. Okay, and so this transformation, this 1/2 inside, is actually a horizontal stretch by 2. And so all of our x distances are going to be 2. And so this point, we're going to go over 2 to get the 1. And then over 2 more to get the 4. And then over 2 more to get the 9. So horizontally stretched makes it look wider. And then our last step is to move it down 6. So take this graph and move it, oh no. Down 6. So now it's at 0, -6. Okay, and then you can tell this is a reflection across the y equals x line. And so if you're starting with a negative square root, you would have the part of the square root that's down, and then your inverse function would be the left side, and then those would still be reflections. Okay, and so that's very important to remember your domain restriction when you're starting with square root. Starting with a positive square root, you're ending with the right side of a quadratic.